Knapsack problem. There are two versions of the problem. 1. 0 to 1 knapsack problem and 2. Fractional knapsack problem. 1. Items are invisible. You either take an item or not. Solved with dynamic programming. 2. Items are divisible. You can take any fraction of an item. Solved with a greedy algorithm. 0 to 1 knapsack problem. Thief has a knapsack with maximum capacity W and a set S consisting of n items. Each item I has some weight Wi and benefit value Vi. All Wi, Vi are W are integer values. Problem. How to pack the knapsack to achieve maximum total value of packed items. Goal. Find Hi such that for all Hi equal to 0, 1, I equal to 1, 2, n. Sigma Wi Hi less than or equal to W and sigma Hi Vi is maximum. 0 to 1 knapsack greedy strategy. Example 2. Item 1, 2, 3, 4, 5, 6, 7. Benefit 5832,794. Weight 78410464. Knapsack holds a maximum of 22 pounds. Fill it to get the maximum benefit. Knapsack problem brute force approach. Let's first solve this problem with a straightforward algorithm. Since there are n items, there are 2 n possible combinations for items. We go through all combinations and find the one with the most total value and with total weight less or equal to W. Running time will be O 2 times n. 0 to 1 knapsack dynamic programming. P I, W. The maximum profit that can be obtained from items 1 to I if the knapsack has size W. In this case 1, thief takes item I. P of I, W equal to Vi plus P of I to 1 W to V W1. Case 2. Thief does not take item 1. P of I, W equal to P of I to 1, W. Recursive formula. P of I, W equal to P of I to 1 W if Wi greater than W. Max Vi plus P of I minus 1 W to Wk P of I minus 1 W else. The best subset that has the total weight W either contains item I or not. First case, Wi greater than W. Item I can't be part of the solution since if it was the total weight would be greater than W, which is unacceptable. Second case, Wi less than equal to W. Then the item I can be in the solution and we choose the case with greater value. Knapsack dynamic programming. P of I, W equal to maximum of Vi plus P of I minus 1, W to Wi, P of I minus 1, W. Reconstructing the optimal solution. Start at P of n, W. When you go left up, item I has been taken. When you go straight up, implies item I has not been taken. Optimal structure. Consider the most valuable load that weighs at most W pounds. If you remove items J from this load, the remaining load must be the most valuable load, weighing at most W to Wj that can be taken from the remaining n to 1 items. Knapsack algorithm. For W equal to 0 to W, P of 0, W equal to 0. For I equal to 0 to n, P of I to 0 equal to 0. For W equal to 0 to W, if Wi less than W, there is item I can be part of the solution. If Vi plus P of I to 1, comma W to Wi greater than P of I to 1 W, P of I to W equal to Vi plus P of I to 1, comma W to W1, else P of I to W equal to P of I to 1, comma W, else P of I, comma W equal to P of I to 1 W. Overlapping subproblems. P of IW equal to maximum of Vi plus P of I minus 1, comma W minus Wi, comma P of I to 1 W. For example, all the subproblems shown in the gray may depend on P2 I to 1 W. Conclusion. Dynamic programming is a useful technique of solving certain kind of problems. When the solution can be recursively described in terms of partial solutions, we can store these partial solutions and reuse them as necessary.